going. In today's lecture, I'm going to be covering the most mathematically advanced material that I'll be covering this term. It will rely quite heavily on material that draws on, number one, linear algebra, number two, calculus, number three, some differential equations, okay? Although nothing more on that side than we covered in past lectures. And the reason I'm giving this is to help convey many of the motivations for using models like this. Models that may be aggregate, may make a fair number of simplifying assumptions compared to what can be represented within an agent-based model, for example, somewhat more stylized. But they're extremely powerful for the insight that you can secure through mathematical analysis. And I'm trying to convey to you a couple of the major techniques people use to secure that insight in terms of identifying equilibria and understanding the stability of those equilibria. So I'm hoping to provide you with some tools which you'll get a chance to exercise on a problem set for working with these sort of models and for generalizing about their behavior beyond a single run. With a lot of simulations, we run with a particular set of parameters, we observe the behavior for those set of parameters, then we run it for a different set, and that can contribute a lot of insight, but the types of methods we'll be talking about today can generalize, can go from just thinking about one scenario at a time with a particular set of parameters to reason about the possible behaviors over all possible sets of parameter values, to allow you to get insight into possible dynamics of the system under a wide variety of possible ranges of values for parameters. And I'm going to give you a glimpse of that. But I have to admit, there's another covert reason that I'm presenting this material today. And the reason harks back to my days as an undergrad, long ago, in a world far, far away, when I encountered for the first time some of the material that we're going to be talking about here, but in a quite different context. So, for example, linear algebra. When I took a course in linear algebra, I think my freshman year in university, I did quite well in the class. I passed it with a quite high mark. I had mastered the basic mechanics of matrix multiplication and matrix inversion and finding the determinant of the matrix and all that good set of stuff. But to be honest, my intuition for what was really going on was very, very poor. So I viewed matrices as boxes of numbers, sort of an arbitrary sort. And there were these arbitrary rules you kind of used with them that were self-consistent. But I didn't really have any sense of the significance of it. It seemed to me a bunch of arbitrary steps you go through, tick the check boxes, and you finish the algorithm. But I didn't really have a sense of why you'd apply these things, what they really meant. And similarly, when using terms like eigenvalues or eigenvectors, or when talking about differential equations, I didn't really have as good an intuition, although it was better for differential equations, as to sort of what was going on. And the material today, hopefully, will start to convey some of those intuitions. I don't have any illusions about this. Probably for most people in the class, you're not going to absorb it all the first time through, and you're going to need to look back at these slides. But if I had known the sort of things that are being presented today and had it presented in this fashion, I think it could have saved me several years of sort of casting around for an understanding of what linear algebra, the significance was, and it would have allowed me to use it in a much more flexible, rich sort of way. So linear algebra will be front and center of many of the things we're talking about, and its interface with calculus, its interface with differential equations. And I guess a further component there. I used to have a button that said Nerd Pride. I would wear it around. I make no apologies about my status. And there's a beauty here. There's an incredible beauty to this mathematics of sort of consistency and things that link up several different types of concepts in unexpected ways. And some of you might carry away a glimpse of it and might find it motivating enough to take a look into it in more detail. So I don't expect everyone coming out of the class today to have a full grasp of what's going on here. I would encourage you to review it. In the problem set, you'll get a chance to try these methods with a very, very simple little example. Okay? I've also tried to show how you could use tools, in this case Maple. How many people here have used Maple before? Okay, just a few. Maple, like several other systems, Sage, Mathematica, is a very, very powerful symbolic mathematics package. And I give some examples of code in Maple which do the sort of analyses you see here. And you'll be able to use those sort of code within a problem set. Okay? So there's some very pragmatic components to this. Okay, so what I'm going to talk about today is just briefly review state equations. This notion of state space we introduced last time. Again, that notion will prove helpful when we're talking about agent-based models, discrete event models even to some degree. It's a very useful sort of rich alternative to viewing particular variables over time. We're then going to talk about this issue of fixed points, equilibria. And we're going to talk not only about the locations of these equilibria, where are these points where a system is going to be stable, or excuse me, or where a system is going to reach a sort of equilibrium. But secondly, we're going to talk about the stability. How do you understand whether it's stable at some of these points? So if you have an equilibrium, how do we know if it's very fragile or very resilient, very robust to disturbance? These things matter because we often will want to get a system into a place where, even with a slight disturbance, even if our calculations are slightly off, even if something unexpected happens, it bounces back. It is resilient under those changes. So today we're going to be talking about this issue of stability, and we'll go into quite some. It turns out the basic approach there, the mechanical level, is pretty straightforward. You linearize the system, run the Jacobian, you take the eigenvalues of the Jacobian, and to look at it around a certain point, you substitute in the location, and you look if any of the eigenvalues are greater than 0. And if they are, an eigenvalue is greater than 0, it means it's unstable. Fair enough. To understand why that is, I'm going to present some math. Okay? And that math, ladies and gentlemen, has real beauty to it. Okay. So that's our agenda today. So just as a reminder, we've seen this before. We can represent system dynamics models, stock and flow models as state equations. These are systems of first-order differential equations. First order because we have the first derivative of a state variable at each successive element on the left, dx dt equals this, dy dt equals that, etc. On the right-hand side, we have the derivatives, which are the net flow into or out of that state variable. And we can represent systems of arbitrary order. I noted that if we have a high-dimensional or a high-order differential equation, we can represent it as a system of lower-order differential equations. So we've seen this before. We have incidence, we have recovery, and we've noted that key component there. And we can map it with a given flow mapping to two elements in here representing conservation. Right? We saw this last time. This is the first order delay, for example, associated with recovery. The number of people here divided by the mean time to recovery. And this term here was associated with this term for contact and contagion, assuming a sort of mixing, a random mixing on the one hand between infectives and the other hand between susceptibles. By random, I mean we're not assuming that any one pair of individuals is any more likely to meet up than in the other pair. And it spreads between these in a process called mass action. It's kind of bumping of infectives against susceptibles in a kind of random way. And as we'll see with agent-based modeling, it's a simplification, and sometimes it's more distant from the reality of the situation. But that term was associated with this element. Okay. That was just a review of that, and we're going to use that as an example for some of these methods. The other notion I introduced was something called state space or phase space, and the note here is we can define a space that where conceptually the coordinates of that space, each coordinate is associated with a particular state variable. And at a given moment in time, the system occupies a point, a single point within that space, representing the values of its state variables at that time. So if we had something like this, susceptible, infected, recovered, we'd have a point in a three-dimensional space which might represent the state of the system, how many susceptibles, how many infectives, how many recovers at that point in time. And if we were to consider the evolution of the system, simulating the system forward through what amounts to numerical integration, the system would evolve over time. It would evolve, and often it will go towards some fixed point, shown here. So this is an example, three-dimensional state space. And in general, if we have n state variables, we will have n coordinates of that state space, one for each state variable. Any questions on that? Because that much has been reviewed. Questions on that? So I'd like now to start going into some material that I touched on last time, but I didn't fully explicate. And that had to do with identifying fixed point locations. If we want to find these locations of equilibria, the equilibria are defined by a certain characteristic. What is that characteristic? It's a characteristic that the state variables are in stasis. They're not changing anymore. They're going up neither up nor down. In other words, the derivatives of them are zero, right? That's the definition of an equilibrium. Given state variable, say the number of susceptibles, it's not going up. It's not going down. It's in equilibrium. So it is for I, say so it is for R. Now we can find the location for these fixed points, for these equilibria, by solving for the values of the state variables. So in our case, SIR, let's say. Solving for expressions of them in terms of the parameters, ideally expressions, ideally formulas for each one in terms of parameters at which the derivatives are equal to zero. Okay. And generally the locations of these fixed points, and there's typically going to be several of them, the locations of fixed points will depend on the parameter values of the model. So changing the parameter values will change where the fixed points are. Now, in some really interesting cases, and we may see a glimpse of this later in the class, actually the number of fixed points depends on the parameters. How many fixed points there are. We can get this interesting phenomenon called bifurcation, where the system may go for certain parameter values, it will have only, say, 2 fixed points, and then maybe it will go to 4 fixed points. Because we have a bifurcation associated with a square root of what turns out to be a negative number, and it has 2 complex conjugate roots, or what have you. We won't go into that right now. If we want to solve a system for fixed points, if we have a system with n state variables, we have typically n constraints, 1 for each derivative. So we have s, ds dt equals 0. That's 1 constraint for the s variable, and we're going to have n constraints and n unknowns, and we'll typically have n fixed points. Okay, it's actually not always true because of certain issues. Well, typically, though, that's a common value. And the larger the number of state variables, the larger number of fixed points. And generally, we prefer formulas given the state variables, the values of the state variables at equilibrium. In other words, at these fixed points in terms of the parameters. And to do that, we solve these constraints. We set the derivatives equal to 0. We solve for SIR, for example, in terms of those parameters. Now, it turns out that This is straightforward for small systems where it's polynomials on the right-hand side. Maybe it's first order delays, maybe it's s times I terms, etc. But in general, and as the number of equations goes up, and as the complexity of those equations, like maybe they involve transcendentals, like x on the right-hand side, dsdt equals, or sine of s, or what have you, then solving these things in so-called enclosed form, getting a formula for where the fixed point locations are, where the equilibria are, becomes not possible. We have to do it numerically. Okay. So for a given fixed set of parameter values, known parameter values that have exact values, we can figure out what the fixed points are for that. And we just run some numerical algorithms that would do root finding, essentially. It just searches for the values of si and r for which those derivatives are 0. Okay. And this is a numerical search. So, for example, for our system, we might have a system like this where, for example, we have some SI terms. In this case, we'll assume that birth rate equals death rate for simplicity, because if you have a constantly growing population, the population's birth rate is greater than death rate, it's never going to reach an equilibrium. It's just going to keep on growing. So for simplicity here, we might assume that those two are equal. So birth rate here flowing into susceptibles, omega times n. Omega is a sort of number of people born per member of the population of birth rate. And this is a death rate here, omega minus s. So that's some number of people dying per unit time. And if we have a system like this, we might compute the fixed points by assigning these derivatives to be 0. Incidentally, because it's a fixed size population, we could simply treat r as n minus s plus I. R is just the remainder of the people who aren't in either of these sums. And that will simplify the size of the increase sum. In any case, the key point here is that to find the fixed points, we set these derivatives as given by these values here equal to 0, and we're going to solve. We're going to solve for I, and we're going to solve for s. Okay. In terms of these various parameters, things like n, omega, c, beta, that sort of thing. And just to walk you through this should be something that people here are comfortable with. We might start with this equation, factor the terms, so we pull this I out. All I did is pulled the I. Notice there's an I for each of these, and I pulled it outside. And that suggests two ways that this term can be equal to 0. One way is that I equals 0. Another way is this thing equals 0. Right? Yeah. So, okay, one way is I equals 0. Now, if I equals 0, then this thing equals 0, and so we must have, if omega n minus omega s equals 0, then it must be that s equals n, right? So in short, that fixed point, just sort of walk you through that informally, is this one here. S equals n, as derived from that thing, I equals 0, and r equals 0. One fixed point. You see that? It's a fixed point precisely because these derivatives are 0. Now, that's a particularly important fixed point in the sense that we have a perfectly healthy population, and there'll be a very interesting question as to how stable it is. If that proverbial person flew into the Saskatoon airport, would they cause an outbreak? Here we have the entire population in the susceptible stock, and it's kind of a trivial fixed point in the sense that not much is going on. We don't have any contagion going on at all. But it's an important one. It's an extremely important one. So that's one fixed point, where I equals 0. Now, if we say, okay, now we want to deal with this case where I is not 0, then this term, this term here, has got to be 0. So we're gonna go through that step, derivation of fixed point 2. Okay, We're going to take advantage of the fact that I is non-zero. We already handled the I equals 0 case. We're going to derive a formula for I in terms of S and various parameters. And actually, first we're going to derive a formula for S in terms of parameters, and then derive a formula for I in terms of S. Then substitute this first one into that one so that we get a formula for I as a function of parameters, and then we're going to simplify the formulas. Okay, so that's the broad step we're taking just due to the nature of the particular equations here. Here we already dealt with the case I equals 0, so we're going to deal with the case where this other term is 0. And we can just rearrange things. Here's our S. There ain't any I here, so it's particularly simple. So we can bring things over. And this is the term that we get, which incidentally we can re-express as 1 plus mu times, this mu times this thing. And then pull a mu out here. So in any case, we'll see a slight rephrasing of that later. But here we've derived S, so we've gone through the first of these right here. Now we're going to derive a formula for I in terms of S, and specifically we're going to use this one here. So to get I in terms of S, we can isolate this I, bring all the S's on the other side, and we'll then have a formula for I in terms of S and the various parameters. All we've done is kind of simple algebra. No big surprises here. A little bit messy, and then we will reminder we have a value for S already, and we could just substitute that into this formula we found for I here. We'll just substitute in for these values of S right here, and we could simplify and get this. And it turns out that there's an intuition here involving a sort of interaction about demographic processes and recovery times. That's kind of interaction. That's kind of interesting. It's really their relationship to each other that's most important, rather than any value in particular. But here's the rearrangement, and I've sort of rearranged things here to have somewhat nicer expressions for these things. This guy here is actually. Does anyone recognize what this is? Can anyone tell me, based on this model, what is this? C times beta times mu. What does that represent? Anyone? Close. Very close. Very, very close. What is mu, though? What is mu? Can you remember? Mean recovery time. And so we actually have, what is C again? Contacts per unit time times mu, be total contacts over some period of infectiousness, right? Times beta, that's a chance per contact or transmission. So this is actually the total number of infections that a given person that's surrounded purely by susceptibles. If I'm an infective and I'm surrounded purely by susceptibles, which happens to be the case right now, so let's stay back. If we have that case, then this is an expression for the total number of people I will infect on average before I recover. C, because I'm mixing with some total number of C people per unit time. Now here, all of them I'm going to assume are susceptible. That's kind of the worst case. It's in the initial case where surrounded by susceptibles, a whole class of susceptibles before me, just waiting to get infected. And so that's C, and then times mu. So that was C times mu, the total number of people I'm going to come into contact with over the course of my illness. And then beta is the chance I'm going to transmit to each other. So surrounded by all these susceptibles, how many am I going to transmit to over the course of my illness? So that's actually a very, very important term. And we have some terms here involving mu and w that have some physical meaning, but that's not my goal here because we have limited time. My goal is to help you understand how we can go beyond this and get an understanding of stability as well. So let's talk about some pragmatics here. Remember that closed form expressions for fixed point locations are not always available. If we have enough state variables, or we have non-polynomials on the right-hand side, generally not going to be able to get that. And then you need it numerically. The second issue is it's really good practice to double-check solutions for fixed points using symbolic mathematics packages. So here's some Maple code where I use the solve function. And for some of these, you may have to do in Maple with some library name, some package name, and we'll import all the methods for that packaging. So I'm solving here two equations. These are the equations associated with stability. These are the derivatives here. I'm just plugging in those things which we had had back here. I'm just plugging these guys, these two guys into Maple, and when doing that, I also have to specify what do I want to. I want to solve for what in terms of the other thing. So here I'm solving for S in infectives. I wrote out infectives because I means something different from Maple. I means square root of -1. So here I have a solution, and it spits these things out, which happen to be the same things we just brought for you. Okay. Spits them out rather faster than I did. So here, the first of these equilibria is associated with the so-called disease-free equilibrium. Here is a situation where we have entirely susceptible population, no infectives. We'd like it to be in that state if we can make it stable. Because if it ain't stable, it's just kindling, waiting to go off. And then it's better to have some recovered around to buffer against things. But if we can keep it stable, if we can be on top of things fast enough, or practice good enough hygiene or what have you, that the infection will just die out, that's a good state to be in. And we're going to look at how we compute stability. This other one is the so-called endemic equilibrium. This is the equilibrium once a disease, if it catches hold, where it's going to end up sort of asymptotically. Remember we saw that last time in terms of the a so-called open population, a population with birth and death going on. What happened? Does anyone remember? What was the curve like for the case where we had a closed population? If we had a situation where an outbreak that an outbreak wouldn't be snuffed out, what did it look like in terms of the number of infectives over time for a closed population? Population that includes no births and deaths. Anyone? Number of infectives did what? Yeah? Good. That's right. That's right. And actually it goes, this one goes arbitrarily close to 0 over time. The number of susceptibles here will generally be very high, and then it will start coming down during this period, and it'll actually start leveling off to a value where typically it won't go to 0. Number of susceptibles, eh? I'm probably not drawing this quite properly. There's some inflections I'm not capturing. Okay, so how about so this is for a closed population, closed. We have some remaining susceptibles at the end, like some wood that didn't get consumed by the fire. Okay, how about for an open population? There? What do we see? What do we see? Okay. Yeah? Okay, and then? Okay, yeah, then it might rise again, and then something like that. And there's some interesting delay dynamics associated with the susceptible population. Susceptibles getting drained by the infection, but it's getting refreshed by births, and so there's some dynamics associated with that, which allows the susceptible population to go down, and then it kind of rebuilds up. It rebuilds up above its sustainable point, and then it's going to start going down again because of this outbreak, and it builds up, etc. Okay, that's good. This is ultimately going towards a point where we have some number of susceptibles and some number of infectives in the long term. Okay, and it's an equilibrium. How stable that equilibrium will be will depend on the situation. So now we're going to talk about this issue of stability. So any questions about this issue of identifying the fixed points? That is something I want you to be very comfortable with. This idea that you set the derivatives equal to 0, you solve for s, you solve for each of the state variables in terms of the parameters. Does that make sense to people? Okay. Typically that's a pretty straightforward operation if you have simple sides on the right-hand side. I made some simplifying assumptions here in terms of births and deaths being comparable because I want to be sure there was some equilibrium. Otherwise, if birth rate way exceeded the death rate, population would just go up without limit, for example. And sometimes you have to think about those things. But particularly with tools like Maple, it's pretty straightforward to do that. Pretty straightforward conceptually for why we do that. This next point where we're going to spend the balance of our time is much more tricky. This is really where the rubber's going to meet the road in terms of some of these techniques I mentioned. And this has to do with how stable are these components. If we want to find these equilibria, are they things that attract the system given some parameter values, or are they things that are unstable and lead to divergent behavior if you get near them? We're interested here at perturbations because our models are imperfect in part, and they may be slightly off. We may have external disturbances which we didn't anticipate, and we'd like a system which is not fragile, a system which is resilient. Unstable systems, we may have a fixed point. It may be stable just like that a meter stick that was balanced on the finger, but that was an unstable equilibrium. A slight deviation, a slight whiff of wind one way or the other. If I had sneezed, it could have knocked that over and it would diverge. So if it's unstable, the fixed point is fragile. Small perturbation will build on itself in a reinforcing feedback, and we'll see where that math comes from. Okay. If it's stable, the fixed point resists change. It's a balancing feedback. The system settles into, pulls it back and brings it back into this equilibrium. And to develop the intuition here, we're first going to deal with a 1D case, a one-dimensional case. Okay, we're going to get to the situations where we can generalize to arbitrary numbers of dimensions, but to develop the basic intuition of why we do things, we can look at the 1D case first. Okay. So suppose we have a situation like this. We have some dx dt equals f of x. Now, in the course of our discussion of system dynamics, we've seen different f of x's. We've seen constants over here. We've seen situations where it's linear term over here, like dx dt equals minus alpha x, something like that. And in general, in the system dynamics package, we could specify an arbitrary function here. It'll also, by the way, could be a function of t. I didn't include that in here, but it could be. Now, what I want to note here, I want to emphasize fixed points occur at values of x, points we'll call them x sub 0, where f of x equals 0, right? We have a fixed point. We're considering a given point x sub 0 where f of x sub 0 is 0. Then we have, by definition, a fixed point, because this is 0. And this is a scalar. I'm just dealing with a scalar. This is just a number, 0. And dx dt equals 0, so it's in stasis. It ain't moving, right? And to develop the intuition that will carry over to the multidimensional case, we're going to look for the criteria for stability of a fixed point. Okay? If we have a fixed point where dx dt equals 0, under what conditions will it be stable? Okay, so let's suppose that we have a dx dt equals f of x, and we're going to visualize that f of x is a function of x. Okay. So here's x on the x-axis and f of x on the y-axis, and I've drawn this out sort of some arbitrary function of x. Okay, and you'll notice that it crosses this at x sub 0. Why does it cross it at x sub 0? Why does it have to cross it at x sub 0? Because I already told you that. Why? F of x 0 equals 0. Yeah. So that's why I cross it. That's a non-trivial point that we'll get back to in the multidimensional case. But so the question here is this stable? If we have this situation, dx dt equals this. Dx dt is describing sort of how a point moves along that axis. If you plunk it down, it will be pulled one way or the other by this dx dt. So I'm asking, is this point stable? So if we situate ourselves at this point, there ain't no change. But if we perturb it, if we were to knock it off slightly to the right or slightly to the left, is it just going to diverge? Or is it going to be knocked back to that point? It doesn't have to make that noise. So is this stable or not? Okay. Could we give an explanation?
If you drop a little bit below,
Yep.
so if the x values a little bit below,
Yep.
then it will move onward.
Yep.
And so we'll move back.
Good. And if we move to the right,
Then we'll make that.
pull you back. And you know, if you knock it, it might pull it back. Depending on how the slope of this, it might pull it back sooner, it might pull it back, take a longer time, but fundamentally it's going to pull back to this point. Does that make sense to people? So to be clear again, if you were to sort of be less than x sub 0, if you have an x that's less than x sub 0, you plunk down, say, right near here, when you feed it in here, we have, okay, we look up f of x, it's some positive number, so dx dt is some positive number, so that means over time x is going to be increasing, right? It's going to pull it back this way, be increasing, right? Does that make sense? And if I plunk it down by contrast, or I knock it out of here just to the right a little bit, here, knock it out, then I look up f of x, it's some negative value, so dx dt equals some negative value, so x will be going down over time, right? Dx dt means declining over time. Does that make sense? Okay. Okay, so in short, this is stable. This is a stable situation. Now, often what we want to do here is to reason about small perturbations, small knocks around that point. And the way in which we do that is we typically zoom in, so to speak. So we're dealing just with the vicinity of that point. And I've shown that with a little red line here, okay? And what I'm arguing is that what really matters here is the slope of this red line, this constant slope right around x sub 0. This other stuff, this kind of weird bend to the left and so on, that really isn't germane if we're talking about little nudges and how a little perturbation, say one person coming into the Saskatoon airport, may lead to an outbreak or to die out. That's not so germane, these kind of macroscopic things way out here. If we were somewhere else in the system, they'd be germane. But if we're right around this point, what really matters is this kind of line around here. We can express the function around that point. That's what this notation means. This is f of x around x sub 0 as approximately the value there, which is 0, plus the derivative there, that's the slope of the line at that point, times x minus x sub 0. This is just a constant that's representing the slope of that line, right? In this case, the slope is negative. This is going to be a negative value times x minus x sub 0. So if I'm at x here, I consider the gap from x sub 0. That's how far down, and then I multiply it times this slope. That's how far down I go here at f of x. That gives approximately f of x that pulls it back. So what we're talking about here is something where if we're right around x sub 0, this line is where it's at. I mean, this sort of linearized thing right around that point. That's what really matters if we're dealing with small perturbations, okay? So the slope here is df of x dx, sort of at that point. It's just the slope at x sub 0. We've just zoomed in, zoomed in there. The question is it stable? Well, it will be stable under certain conditions. Here it's going to be stable for reasons that we're talking about. You go up here, you're too big, f of x is negative, therefore dx dt is negative, therefore it's going to pull you back towards x sub 0. You go off in the negative direction, So x is smaller than x0. F of x is going to be greater than 0. So dx dt is going to equal something greater than 0. So it's going to be increasing x back to this point. And it's really the value of that slope. It's the linear sort of component of the term, the f dx. That's where it's at. Right around that point, that's what matters. You look in far enough, it's going to look like a straight line. Now, I'm an engineer by training, and it's a funny thing when you mix engineers and mathematicians. Mathematicians love bizarre, kind of weird-ass functions that are strange, things like the devil's staircase, and things that are sort of horribly sort of bumpy and stuff like that. Engineers tend to be very pragmatic, and they like dealing with things that if you focus in for a short enough time period, it's varying smoothly. And I'm not dealing with the mathematician's level of rigor here. A mathematician would walk all over this and say, well, how do you know it's differentiable at that point? Maybe it's a non-analytic function and at different values of the derivative from x left and right side. And I'll leave that to the mathematician. I have some very close colleagues and friends who are mathematicians, and I admire their rigor. But in this case, ladies and gentlemen, we're going to err on the side of pragmatism. And this is a very good, very, very solid thing that's used industrially hugely. So it's not a major omission here. We're typically not dealing with a sort of delightful bizarrities that mathematicians will sometimes trouble themselves with. In any event, moving right along. So here we have this slope. We zoom in enough and we deal with the slope. So it's really the slope that matters right around this point. We're going to be crossing the axis. That's why it's a fixed point. F of x is 0 at this point. And the question is, does this first order term, this linear term here, does it slope this way or does it slope that way? Does it go sort of in a way that rises here, rises this way? If it's this way, then it's stable. If it's this way, ladies and gentlemen, it's not stable. Why? Because if we're above x sub 0, if x is greater than x sub 0, f of x will be positive. Actually, I've said g of x just to avoid confusion. G of x will be positive, therefore dx dt will be positive. Therefore, it will make it diverge even further. It will further increase that disparity. And similarly here, it will further increase that disparity. And it will increase it, ladies and gentlemen, by a faster and faster amount. If we have something like this, if we have right around this point, dx dt equals this thing times that, which I argue is sort of the formula for how this looks right around here, this is just a constant. This df, that's just the value for the slope. It's just the value for the derivative. That's all it is. And we can call it lambda, and we could write dx dt equals lambda times x of 0. And if we want to make it pretty, we can do a change of variables and have have y equals x minus x0, dy dt equals that. But fundamentally, this is what we get. X of t equals x of 0 minus x at times 0 minus x of 0 times e to the minus, times e to the lambda t. Why e to the lambda t? Well, we have this thing here. So it's dx dt equals lambda times this. And we saw before. Do you remember first order delays? We saw this. We've seen this before. It's a very simple system to solve. We dt on that side, pull this under, do the integral on both sides, voila. That's what you get. Okay. And this is with a nice little change of variables, so we don't have to worry about having this sort of pesky thing subtracting it off. We just define it this way. And that doesn't change the system in any appreciable way except to clean it up on the right. Does that make sense to people? So what I'm saying is, around this point, we're going to get an exponential driving this thing. If, ladies and gentlemen, that derivative is like this. The slope is negative. Lambda here is going to be negative. Okay? And it's just going to be like that first order delay. Remember? First order delay, we had dx dt equals minus alpha times x, and we saw a declining exponential. Remember that? E to the minus alpha t. Well, it's the same thing here. We're going to get an e to the minus alpha t. It's going to pull it in. and it's going to suck it back, just like that. And a perturbation, a disturbance from that, will be brought back into line. It will suck it back into order. It will resist that pull. It's just like you get hungry, you're going to go get something to eat, and it's going to make you less hungry. It's a balancing loop. By contrast, ladies and gentlemen, if we have a situation where we have this sort of situation, we're going to have a lambda that is positive. And we're going to get a divergent situation where this thing is going to diverge faster and faster away. And we're going to get, just like we saw quite a few lectures ago now, with reinforcing feedbacks, they have this divergent behavior. Faster and faster growth, that's exactly what you're going to get around this point, because you're going to have this, each little change leads to a faster change yet, faster change. The further you go, the faster and faster your rate of change will be. The further and further out, the faster your rate of change away from this point. So you're going to get this sort of exponential divergence, okay? Does that make sense to people? Okay. So here what we're dealing with is a case in one dimensions of stability. And what it came down to, ladies and gentlemen, around a fixed point, because the value at that fixed point of f is 0, what it all came down to is that first derivative around that point. Not to say that if you go far enough out, weird wiggle things just won't wiggle away in strange and delightful ways. It may. But around this point, you get this kind of exponential divergence or exponential convergence, sort of and associated with stability in a balancing loop right around that point. Okay, that's what it came down to when we had a 1D case. And in general, if we have a fixed point in n dimensions, we've been dealing with one-dimensional case, and it all came down to the first derivative. And ladies and gentlemen, so it is with n dimensions. It's all going to come down to the first derivative. But there, you will enjoy the pleasure of acquaintance with a matrix. Matrix because we're dealing with n dimensions vectors. That represent each successive state variable. And you're going to have a matrix which is going to operate on those vectors. And the equivalent of a first derivative in terms of multiple dimensions, when you have a vector differential equation, is a Jacobian matrix. Okay, it's just basically dealing with the first order derivatives. Okay, it's the linear term. And we're going to see where that comes from. Okay? So what basically the phenomena here, you're going to linearize the system at the point. You're going to, just like we linearized it here at x0. Okay? We linearized it around here. Okay? And then what we're going to do, we're going to take what are called the eigenvalues of the Jacobian matrix. And to understand that is going to require some explanation. Why the eigenvalues? It turns out because they give you these lambdas. Okay. The eigenvalues are things of beauty. The eigenvectors are these quantities associated with the first order differential equation that are going to just pass through it and be multiplied by eigenvalues. And the eigenvalues are associated with each of these lambdas. The lambdas with the eigenvalues. And you're going to have a set of them, one for each state variable, typically. Okay, a set of these eigenvalues. Now, sometimes they turn out to be the same, but often they're going to be quite distinct. Okay, so you're going to have the eigenvalues of this so-called Jacobian matrix. And those are going to express these kind of linear terms around this fixed point. What's increasing what in what direction? And then it's very simple criteria, folks. Once you take the eigenvalues, and that can be done mechanically. Both these previous steps can be done mechanically. It can be done in Maple. You just crunch it away, and it spits it out. Now, the real component of any eigenvalue any of them, is greater than 0, then it's unstable. Unstable. Divergent. If the real component of all eigenvalues are less than 0, it's going to be stable. And if the real component of all eigenvalues is equal to 0, you're going to typically have imaginary eigenvalues, which are fun things to deal with. But they're going to be associated with limit cycles. So they're going to be associated with a situation where you're going to have a fixed point, and instead of sucking things in, just like that, and in one direction, and maybe it sucks in from both directions. It's like a giant black hole sucking in from other directions, or maybe it sucks in from one direction and spits out in another. Here we have two negative eigenvalues. This would be lambda 1 less than 0, lambda 2 less than 0. It's just sucking in from the vicinity. Things come near it and they get sucked into this vortex. Well, it's not a vortex. It gets sucked into a point. Here we might have a situation where one eigenvalue is less than 0, and we are sucking in along that direction, and one eigenvalue is greater than 0, and we're spitting out along that direction. So we're sort of pulling things this way and then driving them out that way. So we get kind of this space that pulls down in that sort of way. Alternatively, we might get a situation where, for example, we have two eigenvalues, both greater than 0, in which case we'll get divergence along two areas. And we may get a situation where the eigenvalues are actually, the real part is 0, and we may get, for example, limit cycles around this point. So we'll get these kind of orbits. As we approach this point, we'll go into an orbit around it. And we can get varieties of these. For example, we may get a situation, in fact we saw that last time, where the eigenvalue's real component is less than 0, but it had imaginary components too. And so what would that look like? What do you think? What would be a mixture of this in this situation where we're sort of sucking in from the directions? What would a mixture of these look like? We saw it last time, actually. It's a spiral. And it sucks into the vortex state there. Okay. So here we might have the real components of these eigenvalues equal to 0, and it's a limit cycle. And in other cases, we'll have real of this less than 0, and we'll have some imaginary components as well that will lead to these cycles. By the way, does anyone know why is an imaginary component lead to these kind of cyclic patterns? Anyone? Yes. Now, I don't know how they write it here in different areas of the campus. I'm writing I as the square root of -1. Some people may write it as j, which is common in some areas of engineering. So we can decompose this into, can anyone give me the formula? I'm going to write e to the I theta t, or e to the I theta. Can anyone give that to me? Good. And it has to be that way, right? Because if theta is 0, it's going to be e to the 0. And so you need a cos theta and then plus I sine theta. And that's why you're going to get these, when you have imaginary components, the eigenvalues, you're going to get these kind of different forms here. We can get oscillations. We can't get that. I believe this is the case. I don't think we can get that in 1D. I think you need at least 2D to get that. In any case, that's why we see these kind of cyclic patterns associated with it. As time goes on, it's kind of going around this in a way just as theta is evolving over time. Here will be e to the I theta t, and it will be cosine theta t plus I sine theta t, something like that. Okay, does that make sense? Yes?
These three conditions,
yeah. What
happens when we have one eigenvalue equals 0?
Oh, it's a good question. Yeah, I didn't. If you have one equal to 0 and the others, actually you cannot, because they come in complex conjugate pairs. Okay, so you could have one equal to 0, in which case that's going to be a steady state mode. But if they're imaginary, things come in complex conjugate pairs. So if you have an A plus IB, you're going to have an A minus IB out of it as well. But you could have equal to 0 exactly, in which case you're going to actually have a steady state value for a given for a given state variable. You're going to actually have some. It's going to be essentially e to the lambda t, where if lambda is 0, this is equal to 1. And you're going to have some steady state value that's going to lead to a persistent value that doesn't vary along that axis. So you won't be changing this way or this way, but the other values may be changing. So in other words, you might get a situation where that value, let's suppose it's this axis, you won't be changing that, but the other values may be changing. So this one will sort of retain its value. Okay. So the others will dominate the dynamics. Yeah. Good question. Any other question on that? So we've dealt with the one-dimensional case. Now I'd like to see how this applies to the 2 dimensions, okay, or to more than one dimension. So to understand why this procedure works, we need to bring in some components. Generally speaking, folks, we have these state equations. The left-hand side being state variables, the right-hand side being derivatives of state variables. We can express the state variables in a vector. We can express it like this. Here's our state variables, s and I, and we could denote that with a vector, x with an arrow over it. And then what we're going to have is dx dt, that's a vector of s dot I dot in the lower component equals some vector function of this thing here. And this is the vector function. These are just the formulas that were on the right-hand side. This was the formula on the right-hand side for s dot. You remember that? S dot. And this is for I dot. They're just each of those components. So here we have function of a state variable, and this is the function of the state variable. It's itself a vector. It's a vector function. That's why you put the f over with the arrow over it. And I'm going to be a bit sloppy with putting the arrows over matrices and functions sometimes. Okay, so just a reminder: when we did linearization in 1D, we could consider a given function around a point, and we could write it as, if we linearize a function with a point, we could do a Taylor expansion and write it as f of x sub 0. Plus, so consider this function around a point, f of x sub 0 is the basic term, plus this is the slope times x minus x sub 0, plus second derivative over 2 factorial times x minus x squared. This is just the Taylor expansion of this function around this point, x0. Yeah? When we have that sort of situation, we argued that if we focus enough in detail and we're not dealing with functions that physicists and engineers would call degenerate functions or functions that are misbehaved. For small enough deviations, x minus x sub 0, x minus x sub 0 will be vastly larger than these terms. So right around x sub 0, these two terms dominate. And ladies and gentlemen, if x sub 0 is a fixed point, what term do we have left? So I'm saying around x sub 0, we can cut off these higher terms if we're looking right in the area of it, because x minus x sub 0 might be 0.001, and x minus x sub 0 squared is 0.00001, and so this is hugely larger than that. We can ignore that right around it. And here's our first derivative, and here's this term. If x sub 0 is a fixed point, what term do we have left? What term disappears? What term goes away? What term is 0? This one. It's 0. That's by definition. It's the fixed point of f. Okay, so then all we have left is that term, right? So that was linearization in 1D. Ladies and gentlemen, we could perform linearization in multiple dimensions using matrices, using vectors representing our values. Here we had just a single value, a scalar, x. Here we're going to have a vector, like SI, or SIR, or SEIR, what have you. It's a vector. But we could also linearize a function in vector space around this. So if we have if we linearize around a point in this vector space, which will be our state space here, the value of f, this vector function around the state space, with the value at that point, plus we go out, and we're evaluating at some point x, right around x of 0. If we go out in a certain direction, x is displaced in this vector in a certain direction, then we have this term here, which is a matrix, and it's called the Jacobian matrix. It basically expresses for a given deviation, a given direction, how far off, how much do you have to increase f? So if you're off in this direction, how much does f have to increase in its first component, and its second component, etc. If you're off in this other direction, how much does it have to increase? And then we have some higher order terms. This is, ladies and gentlemen, this is nothing more than this generalized to this vector notation. This is just capturing how much do each element of this f of x, like how much does dx, the s dot increase if you go off in a given direction from x of 0, in a given direction, for each little increment you go off in that direction, how much does s dot increase? How much does I dot increase? How much does R dot increase? That's all this is giving you, okay? And then we've got some higher order terms, which include things like the Hessian, and probably mathematicians have various names of great mathematicians that I don't know for higher order ones yet. Mathematicians have all these great names for matrices. But this is the Jacobian. And ladies and gentlemen, it took me many years. I met the Jacobian early on, fairly early on, during my undergraduate career. And at first he scared me. But then I got more comfortable with it. And soon I realized that it's a thing of beauty and a joy forever. So the Jacobian is something I'd like to make your acquaintance of. We'll recall here. Well, let's talk. Well, maybe I'll continue on this. We'll come back to the Jacobian in a second. But I want you to remember, at a fixed point, f at that fixed point is defined to be 0, right? At a fixed point, this term is 0. At a fixed point, there is no change in s dot. The s dot is 0. No change in I, so I dot is 0. R dot is 0, however many terms you have. All those are 0. So this term is going to go away around a fixed point, okay? That's what defines it as a fixed point. So at a fixed point, this first term goes away, and all we're going to have is this term. And by the same argument we used in 1D, if we get close enough around x sub 0, quite close, then these higher order terms go away, and basically all we're left with is this guy here, which is our friend the Jacobian. He's all you got left. Got to make his acquaintance. He'll be a good friend. So there you go. This is basically the Jacobian times this deviation. So if you're considering what is the value of f at the next, what is the value of s dot and I dot and E dot and R dot, or however many state variables you have, here you're saying how do those vary? This describes how they vary with these deviations around x as vectors, okay? We're going to write this notation of like x sub I to denote the ith element of x. And I will leave it unsaid as to whether I starts at 0 or 1, but I think we'll start at 1. Just we're in applied mathematics, and I will cede my rights in numbering things to the mathematician. So I will start at 1. So x sub 1 will be the first element of x, of a vector x. So if we have a vector SIR, we'll call it x. or vector s dot, I dot, and r dot, the derivatives of s, I, and r, then the first element of it will be x sub 1, and that will be s dot. Second derivative x sub 2 will be I dot. Okay? And similarly, we'll write f as a vector function of x, because we have this as a vector x dot, s dot, I dot, r dot equals some vector function of x, of s, I, and r. We're going to have here f sub I for the ith element of the vector. Here's the Jacobian matrix. Behold a thing of beauty. This is called the Jacobian of f. Okay. Now the point here is that I've chosen this way to write it, but it's denoted commonly as Jacobian. And here what we have, folks, makes a lot of sense. So in the top row of this, we have successive derivatives of f sub 1. Okay. Let's just be clear what that is. So f sub 1 here, I think did I introduce it? Did I have a nice slide? Yes, there it is. Here's f sub 1. This is f sub 1, okay? That basically gives the formula for the derivative of s dot in this case. Here's f sub 2. This is the function of this vector, your current point in state space, just like we had f of x when x was a scalar. Here we have f of the current values of the state of the current point in state space, f of si, yeah, and f sub 1 will be this first formula along the top here. F sub 2 will be the second formula. Okay, so along the top of that Jacobian matrix, we are going to have successive derivatives of this component with respect to each successive state variable in turn. So we're going to have that derivative of that formula with respect to s, derivative of that formula with respect to I, derivative of that formula, well, if we had other variables, it would be there. Here are just s and I. Okay. Do I have a nice little picture? Oh, I missed the opportunity to have a little picture of my Jacobian here. I might be able to just show it to you. Oh, yeah, there it is. Look at that. Look at that, folks. Here we have, this is this SIR simplified. Oh, there it is here. This guy. And we're going to take the Jacobian, we have these guys. So here, this will be the derivative of that formula with respect to s. And the next one will be derivative of that formula with respect to I. Now, why do we have that? Well, we're going to have, when we apply the Jacobian, we're going to multiply it times a vector of displacements. We're going to say, how much are we off in the s direction? And by multiplying that discrepancy in the s direction times this slope, that gives how much this formula will increase given a unit discrepancy in s, we will get how much does that first element, s dot, have to increase. Similarly, for the derivative of that with respect to I, that's going to multiply by the second element of the vector, the change in I, and we're going to multiply that times the slope. It is nothing more than the multi-dimensional version of, and where do I have that nice slide here? It's nothing more than the multi-dimensional version of this guy right here. We're just going to take the difference of where we are from this fixed point, and we're going to multiply by the appropriate slope. That's all the Jacobian is doing. So the first row of the Jacobian is just doing that for s dot. It's doing that for the formula for s dot. It's saying how much does s dot vary, what's the slope of s dot with respect to changes in s multiplied by the discrepancy in s from the fixed point. How fast is it changing, s dot changing with respect to changes in I times the discrepancy in I. And by summing that up, by multiplying times the discrepancy in s, the current s minus s dot s0, the value at the fixed point, and then so that times this term, and this term times I minus I0, the value at the fixed point, we'll get a sum up of how fast s dot is changing overall. In other words, the rate of change of s dot, which is what we're seeking. That would be just like the linear slope. It allows us to determine what is s dot. Similarly, this guy will allow us to determine what is I dot. etc. Okay? So the Jacobian matrix is basically just representing, it's a fancy thing that represents how quickly each these terms within this derivative vector here are changing with respect to each of these state variables, s and then I, s and then I, on the second value of the Jacobian matrix. Now, notably, folks, the Jacobian matrix will, in general, have values that depend on s. So it's a matrix that varies. Its entries vary as you're changing your location in state space. You'll notice the Jacobian matrix has these quantities which depend on s, and I guess this one doesn't depend on I, but you could imagine in some cases it can depend on I. So these are the entries of the Jacobian matrix. They say how quickly is this guy s dot changing with respect to a unit change in s, and with respect to a unit change in I, and then how quickly is I dot changing with respect to unit change in s, unit change in I. Does that make sense? Okay. The Jacobian is arguably this thing that's the element of the of this lecture. So if you folks haven't thrown me out yet, it's probably a good sign. Okay, now the key thing here, folks, and it took me years to appreciate this, matrices are not boxes of numbers. Do not think of them that way. In many cases, they're best thought of as operators. Okay, they're a linear operator. They're just like a function, but it operates in a linear way. Okay. So they operate on vectors. You give them a vector in, they'll give you a vector out. Now in this case, it's a square matrix, which means we give it a vector in of size n, and it gives us a vector out of size n. Okay. And the Jacobian matrix here maps from a vector of si and r to a vector of s dot I dot r dot. Depending on the innards of the matrix, it'll be doing different things, and this is where we get to these things of eigenvalues. Sometimes it will do rotations. It'll take a vector in and rotate, push it a different way. Sometimes it will scale it. These scaled it. So here, if we had like x1 less than 0, it's going to be, again, scaling it down, sucking it down. Faster and faster in just the sort of, well, I shouldn't say faster and faster, in this exactly that sort of first order delay sort of way we saw. So there it's scaling a vector in, pulling in that way. In other cases it skews it, it kind of rotates it in a sort of shear sort of way. Okay, so the Jacobian matrix is this operator, and it gives you the derivatives for each of the state variables, s dot, I dot, etc. The result from small deviations around the point where the Jacobian is valued, around the fixed point. Okay. Displacements in one direction will generally be handled differently than others, and we're going to see where eigenvalues come to that. It turns out eigenvalues are going to be vectors are going to be key to this story. If you have an eigenvector, you can reason about how the Jacobian matrix operates on each eigenvalue in isolation. Because it's linear, you can reason about it in isolation, linear around that point. Okay, so some eigenvalues it's going to suck in, some it's going to expand out. Some situations you may get a rotation around as well. Okay, so in some cases it will be a sort of positive feedback loop pushing out in just the sort of way we saw in one dimension. X dot equals lambda x, where lambda is greater than 1 or greater than 0, pushing out faster and faster. In other cases, it'll be sucking in a sort of negative feedback loop. Okay, now, why does this come down to eigenvalues and eigenvectors? Probably the least thing you want to deal with. Well, it turns out that eigenvectors are nice. They're your friends too, in case someone didn't tell you in math, or in case you didn't believe them. The eigenvectors of the Jacobian matrix are the natural coordinates to describe it. Okay. And if we describe it in terms of them, our life will be much simpler. Those are the coordinates on which it operates independently. So if we deal with other coordinates, we can be doing funky things with respect to multiple things at once. With eigenvalues, we could just think about how much of each eigenvector we have in it, and we know what it does for that particular eigenvector, and then we can sum up accordingly. Okay. So here we're going to decompose a given displacement vector into the components along each eigenvector. And then there's an eigenvalue that describes how it handles that eigenvector, whether it's sucking it in, pushing it out, rotating it, or what have you, and those will then affect the derivatives. So why is it so important that we deal with eigenvectors? Well, we're dealing with right around the point. We have some matrix, which in this case I've written with 2 vectors in the common notation in some quarters. So this is going to be our Jacobian. So Jacobian is going to tell us, for a given displacement around our fixed point, how does this change? How does our derivative in state space change? That's going to tell us sort of where we're going to go. We don't have here the constant term, because it's a fixed point. It's 0 around that point. So we don't have to worry. This is around the point x0. Okay, should have written that. Okay, now if we have this being an eigenvector, then dx dt will just be a multiple of this, and that will allow us to understand whether it's pushing back or pushing out around there. Okay, so generally speaking, what we do is we just switch to a coordinate system centered at that fixed point, just like we did for y for the single variable case. And we have dx dt equals this thing. Okay, this is in that new coordinate system, so we don't have to deal with minus x0 explicitly. And then we're going to decompose x into coordinate times eigenvector. We're just going to express x in terms of the eigenvectors rather than in terms of our normal coordinates. It's just like instead of expressing a lat long, the location on the Earth, you express it instead in the military sort of numbering system. It's just a different coordinate system. Okay. So here we're going to express x as a sum of unit eigenvectors times some constant for each one. So x is made up of so much of this eigenvector, so much of that eigenvector. And to find out those constants, we just take the dot product of x with respect to that appropriate eigenvector. Okay. Okay. Now, because these are eigenvectors, if we take the derivative with respect to that, we have this. The key point here is that if we apply this Jacobian matrix to an eigenvector, what do we get out? We just get out that eigenvector scaled by a certain amount. That's the beauty here, or that's a beauty. Go back and watch the tape again if its beauty doesn't strike you. But if we have an eigenvector and we feed it into this Jacobian matrix, what we get out is the same vector, just scaled, or adjusted. It could this scaling could be imaginary, in which case it's got an additional computation to it. This is just a simple first order ODE now. So if we have x and it's a sum of these things, if we consider with respect to a given eigenvalue, this is what it gives us. We have this unit thing here and here. This is just the differential equation in terms of the c sub i's, and this is what we have. What this is telling us is that the amount of a given eigenvector is varying with lambda. And if you folks should be able to tell me, if I have a matrix, in this case it's Jacobian, times a vector, and it gives me lambda times that vector, what is this lambda called? It's called the, if this is the eigenvector, this is the eigenvalue. It's the eigenvalue. So these are special vectors with respect to it. They're especially easy to work with because A doesn't change them. A just scales them in some sort of way, okay? And here, the most classic thing is it's going to shrink them. So if you have that one of a vector, you're displaced in that direction, it's going to pull you in the opposite direction, or it's going to push you out in the same direction. So again, if lambda is less than 0, it's going to be sucking you in. If lambda is greater than 0, it's going to be pushing you out. So here it's going to be divergent if the eigenvalues are greater than 0, convergent, pulling towards stability if the eigenvalues are less than 0. And it does that with respect to each eigenvalue. And the beauty is that we can decompose any vector into these eigenvalues and apply this. And then our solution will just be the sum of the solutions with respect to each eigenvalue in isolation. So we're just going to sum up how it handles each eigenvalue. So if we know how it handles each eigenvector, if we sum up how it's going to handle each eigenvector, we get the total behavior around that point. Okay. So right around that point, x sub 0, this is going to be the behavior where these k's are just unit eigenvectors of this Jacobian matrix. Okay. Now, there is something just incredibly beautiful that presents this in another way that I stuck in there. And this involves what's called the similarity transform. How many people have seen this before? Similarity transform? Okay. Oh, it's beautiful. But the basic deal here, folks, is if you have an equation like this, if you know your linear algebra, what you could end up doing is expressing that equation, the solution to this system of equations there. Let's suppose this were just dx dt equals alpha x, where x is just a scalar. What's the solution for this? Someone? What's the solution? If we had dx dt equals alpha times x, what's the solution? Yeah. Some initial value times e to the alpha t, right? Well, it turns out that through the beauty of linear algebra, you can just write down the solution associated with this, and it's going to involve an e to the a t, where a is a matrix. Okay. Now you may say, what the heck does that mean? Some may use stronger language, but it turns out that it is a very well-defined meaning. So e to the matrix is just 1 plus. You just do the Taylor expansion in the same sort of way. Okay. And here is the matrix over 1. Matrix squared, in other words, matrix multiplied times another matrix over 2. So we can actually write the solution down immediately in terms of that. And the beauty of this is that if you follow through, oh gosh, it didn't turn out so well. If you follow through the similarity transform, what you can essentially show very straightforwardly is that what you can do is take a given vector, transform it into the basis of eigenvectors. So express it in terms of eigenvectors, in other words. Then you just multiply it times essentially a matrix that's composed just like this, where each of these is a successive eigenvalue. And then you transform it back into the regular basis. So this is a similarity transform. It involves mapping from whatever over here, say x, transforms it into the eigenvector basis, applies this matrix, which is just diagonal, so it's particularly simple, maps it back to the regular basis, and then multiplies it by the initial value of the variable. So fundamentally, ladies and gentlemen, the behavior around a given fixed point behaves according to this equation. It's dominated by eigenvalues, and if these eigenvalues are less than 0, then you will have stability because you'll have these balancing feedbacks pulling in from these directions. If the real component of the eigenvalue is less than 0 and you have some imaginary components, you get these spirals, sort of like we saw last time. If you have purely imaginary components, you get these limit cycles. But fundamentally, it's all about these eigenvalues. Okay? It's all about the eigenvalues. And that is why, when I describe the steps here, and this is going to require a couple things back, and I'm going to break in just a minute here, just about done here. I admire your fortitude. If we go back here, this is the process. So we linearize the system. We determine the Jacobian. We evaluate the Jacobian at the fixed point. The Jacobian can vary with the state variables s and I, just like we saw from my maple here. This is the Jacobian, and it can depend on s. So we evaluate it at the fixed point. We say, for this fixed point, what value? And I can see this done in my maple here. So I eval these eigenvalues at this fixed point, and it spits out eigenvalues at that fixed point. Okay, then, excuse me. So I value the eigenvalues there, and I do it at this point, okay? And then I examine the real components and evaluate whether it's stable. The beauty is, folks, that this evaluation is typically done with for small systems, we can express it all symbolically. So in other words, we'll have values for the, in many cases, we'll have values for the eigenvalues as a function of the parameters. Now that may not seem significant to you, but what's significant about it is it tells you how the location of the fixed points and how the stability of the fixed point varies with parameters. So for some values of parameters, this will be a stable one. Other values of parameters will be unstable. In some cases, this fixed point will be located, way up here at very high values of I. In other cases, it will be located at very low values. So in other words, ladies and gentlemen, by going through this process with sufficiently simple systems, we can identify in concrete terms what the fixed points are in terms of the parameters, and therefore know how they vary as we increase the parameter. For example, as we make our infection more contagious, or people's contact goes up, or the rate of birth and death rises, or as the length of time to recovery changes, we know how it affects the locations of our fixed points, and we can reason about how it affects the stability of our fixed points by reasoning about these the values of these eigenvalues, under what condition they're greater than 0, and under what conditions they're less than 0, etc. So, and under what conditions they're imaginary and therefore lead to limit cycles. So in short, when we have these eigenvalues in terms of the parameters in closed form, it gives us great ability to generalize not from just one scenario at a time, as we'll be running a lot in this class, particularly from now on, but instead allows us to get insight into the overall possible behaviors of this system. I've done this sort of work for some fairly sophisticated systems, and it's surprisingly powerful. You can get a lot of insight into it that will let you go beyond the simple running simulations one after the other and allow you to reason about broad areas of behavior. Today, this has been a huge amount of material I presented. I hope it's provided some glimpse of the mathematical tools that can be applied here. Remember, if you are evaluating these numerically, you will. This will be particularly simple because the eigenvalues will just be numerical values, and you can evaluate these things in a very straightforward thing. If you're trying to get closed form expressions, it often requires a little bit of machinations, but it can also be done for smaller systems. So this is the element by which people will analyze systems, decide if they are stable, decide what components of them are stable, where the fixed points are, etc. This is one of the reasons that system dynamics types of models and the broader field of dynamical systems research makes use of these sort of simplified representations. It's to give great insight, particularly under wide ranges of parameter values, using tools like these. Okay, so I'm going to post these slides and naturally the video, and I hope these comments will be helpful. In your next problem set, you will have a very small example of this where you'll be using Maple to do these sort of evaluations. It'll be much simpler than what you've seen here, and it will involve only 2 elements of the vector. But you'll get a chance to apply these a bit and make use of Maple to simplify the work of deriving the fixed points, etc. Okay, so that's all for today. I'm glad I made this through without sneezing, as I'm currently have reason to believe I'm bereavement. I will look forward to seeing you on Tuesday.